Now we come to chapter 8 module 2. In this module we shall learn some properties of Mellin transform. Let us denote the Mellin transform of a function f x defined by x positive and denoted by curl M of f x, which is capital F s, equal to integral from 0 to infinity f x x to the power s minus 1 dx. This is the Mellin transform of the function f x. Now we shall discuss the properties of Mellin transform. First property is the linearity property. If capital F s and capital G s are Mellin transforms of the function small f x and g x, then Mellin transform of C1 f x plus C2 g x equal to C1 capital F s plus C2 capital G s, where C1 and C2 are some constants. Proof is very simple. We start with Mellin transform of C1 f x plus C2 g x, which is equal to integral from 0 to infinity C1 f x plus C2 g x into x to the power s minus 1 dx, which is equal to C1 integral 0 to infinity f x x to the power s minus 1 dx plus C2 into integral 0 to infinity g x x to the power s minus 1 dx, which is equal to C1 capital F s plus C2 capital G s. Hence, the linearity property is proved. Next is scaling property, which is Mellin transform of f of a x equal to capital F s divided by a to the power s, where a is some positive constant. For proof, we write the Mellin transform of f of a x, and this is equal to integral from 0 to infinity x to the power s minus 1 f of a x dx. This is equal to, after substituting a x equal to t, we can write it as 1 by a to the power s integral from 0 to infinity t to the power s minus 1 f t dt, and this is equal to capital F s divided by a to the power s. Next is translation property, which is given by Mellin transform of x to the power a f x is equal to capital F of s plus a. A is some constant. For proof, we write down the Mellin transform of x to the power a f x, which is equal to integral from 0 to infinity x to the power a f x x to the power s minus 1 dx, that is equal to integral from 0 to infinity f x x to the power a plus s minus 1 dx, and this is equal to capital F of s plus a. So, this is the translation property. Next, we shall find out Mellin transform of some function of x to the power a, where a is positive. Mellin transform of f of x to the power a is equal to 1 by a capital F of s by a. For proof, we write the Mellin transform of f of x to the power a, and which is given by integral from 0 to infinity x to the power s minus 1 f of x to the power a dx. This we can write after substituting t equal to x to the power a as integral from 0 to infinity t to the power s minus 1 by a f t t to the power 1 by a minus 1 dt by a, which is equal to 1 by a integral from 0 to infinity t to the power s by a minus 1 f t dt, and this is equal to 1 by a capital F of s by a. Next we shall find out Mellin transform of 1 by x into f of 1 by x, and that is equal to capital F of 1 minus s. This we have to prove. First we write the Mellin transform of 1 by x f of 1 by x, and this is equal to integral from 0 to infinity x to the power s minus 1 into 1 by x into f of 1 by x dx. Writing t equal to 1 by x, this integral can be written as integral from 0 to infinity t to the power minus s f t dt. This is equal to f of capital F of 1 minus s. Next we shall find out Mellin transform of derivative of a function. Let f(x) be continuous for x greater than equal to 0 and capital Fs be the Mellin transform of small f(x). Further, we also assume that limit x tending to 0 x to the power s minus 1 f(x) equal to 0 and also limit x tending to infinity x to the power s minus 1 f(x) equal to 0 for sigma 1 less than real s less than sigma 2. Then Mellin transform of derivative of the function f(x), that is Mellin transform of f dash x, is equal to minus s minus 1 capital F s minus 1, where sigma 1 less than real s less than sigma 2, provided f of s minus 1 exists for real s lying in the interval sigma 1 to sigma 2. For proof, we start with Mellin transform of f dash x, which is equal to integral from 0 to infinity x to the power s minus 1 into f dash x dx. Integrating by parts, we can write it as x to the power s minus 1 f(x) x from 0 to infinity minus s minus 1 into integral from 0 to infinity x to the power s minus 2 f(x) dx. Now, because of the condition that limit x tending to 0 x to the power s minus 1 f(x) equal to 0 and limit x tending to infinity x to the power s minus 1 f(x) equal to 0, the first term here vanishes and we obtain Mellin transform of f dash x equal to minus s minus 1 capital F of s minus 1. Here real s lies in the interval sigma 1 to sigma 2. A second application of this result leads to Mellin transform of f double dash x, and that is equal to minus s minus 1 Mellin transform of f dash x s minus 1. Applying the previous result, that is Mellin transform of f dash x equal to minus s minus 1 capital F s minus 1, we write this as Mellin transform of f double dash x equal to s minus 1 into s minus 2 into capital F s minus 2, provided limit extending to 0 x to the power s minus 2 f dash x is equal to 0. Continuing in this way, we can prove by induction Mellin transform of nth derivative of f, that is equal to minus 1 to the power n gamma s divided by gamma s minus n into capital F of s minus n, provided limit extending to 0 x to the power s minus k minus 1 kth derivative of f x equal to 0 for k equal to 0, 1, 2 up to n minus 1. In module 2 of chapter 8, so far we have studied some important properties of Mellin transform. Now, we shall study some more properties of Mellin transform. Next we come to the seventh property, which is about the convolution theorem of Mellin transform. Let capital Fs and capital Gs be the Mellin transforms of small fx and small gx defined for x positive respectively. Then capital M inverse of Fs Gs, capital Fs and capital Gs, its inverse Mellin transform is equal to integral from 0 to infinity small f of x by t into gt dt by t as given in equation 1. This is the convolution theorem for Mellin transform. For proof, we write integral from 0 to infinity fx gx into x to the power s minus 1 dx. This is equal to, after writing fx as inverse of capital Fs, we get integral from 0 to infinity gx x to the power s minus 1 ds into 1 by 2 pi I integral from c minus I infinity to c plus I infinity capital Fz x to the power minus z dz. The inner integral is the Mellin inverse of capital Fz. If we interchange the order of integration, that is z integral now becomes the outer integral and x integral is the inner integral, we get 1 by 2 pi I integral from c minus I infinity to c plus I infinity capital Fz integral from 0 to infinity gx x to the power s minus z minus 1 dx dz. Now, the inner integral can be written as the Mellin transform of small gx, which can be written as capital G of s minus z. So that this becomes equal to 1 by 2 pi I integral from c minus I infinity to c plus I infinity capital Fz into capital G of s minus z dz. This shows that the Mellin transform of product of two functions small fx and small gx, which is given here left hand side, that is equal to 1 by 2 pi I integral from c minus I infinity to c plus I infinity capital Fz into capital G s minus z dz as given in equation 2. If we put s equal to 1 in this result, then the left hand side of equation 2 becomes integral from 0 to infinity fx gx dx. This is equal to, right hand side if we put s equal to 1, this becomes equal to 1 by 2 pi I integral from c minus I infinity to c plus I infinity capital Fz g of 1 minus z dz as given in equation 3. Again, if we consider Mellin inverse of capital Fs into capital Gs, then we obtain this as 1 by 2 pi I integral from c minus I infinity to c plus I infinity capital Fs into capital Gs x to the power minus s ds. Now, capital Gs is the Mellin transform of small gt. So, if we substitute in place of capital Gs Mellin transform of small gt, then we can write Mellin inverse of product of capital F and capital G as 1 by 2 pi I integral c minus I infinity to c plus I infinity capital Fs into x to the power minus s into integral from 0 to infinity gt t to the power s minus 1 dt ds. So, inner integral is written in place of capital Gs. Now, interchanging the order of integration, we can write as integral from 0 to infinity gt by t integral c minus I infinity to c plus I infinity 1 by 2 pi I capital Fs x by t to the power minus s ds dt. This step is achieved by simple calculation and interchanging the order of integration. Now, the inner integral is the Mellin inverse of small f of x by t. So, that we can write Mellin inverse of product of capital F and capital G as integral from 0 to infinity small f x by t into gt dt by t as given in equation 4. So, this proves the result. Next we come to another property, that Mellin transform of log x fx is equal to capital F dash s. Here f dash s is the derivative with respect to s. For proof, we start with Mellin transform of log x fx, which is equal to integral from 0 to infinity x to the power s minus 1 log x fx dx. This can be written as, after a simple calculation, that dds of integral x to the power s minus 1 fx dx. The integral is the Mellin transform of small fx, which is denoted by capital F, and there is a dds outside. So, Mellin transform of log x fx is equal to capital F dash s. Next property is to find out Mellin transform of x into f dash x. Here dash means derivative of small f with respect to x. So, Mellin transform of x f dash x can be written as integral from 0 to infinity x to the power s f dash x dx. This we integrate by parts to get x to the power s fx x from 0 and infinity minus s integral from 0 to infinity x to the power s minus 1 fx dx. Assuming that x to the power s fx is equal to 0 as x tends to 0 as well as x tends to infinity, we find that this term vanishes, so that Mellin transform of x f dash x is equal to minus s capital Fs. Next property is that using property given in 9, we can use mathematical induction method to prove that Mellin transform of x to the power n, nth derivative of small fx is equal to minus 1 to the power n gamma s plus n divided by gamma s into capital Fs. In the next property, we shall prove that Mellin transform of x square f double dash x plus x f dash x is equal to s square capital Fs. To prove this, we use the linearity property to write Mellin transform of x square f double dash x is equal plus x f dash x is equal to Mellin transform of x square f double dash x plus Mellin transform of x f dash x. Now, from property 10, we can use this property for n equal to 2, that is Mellin transform of x square f double dash x will be given by gamma of s plus 2 by gamma s into capital Fs. This we substitute here, and Mellin transform of x f dash x can be obtained from property 9, which is given by minus s capital Fs. If we use properties 8 and 9, 10, Mellin transform of x square f double dash x plus x f dash x is equal to s square capital Fs. Next is to find Mellin transform of integral 0 to x f t dt. That has to be equal to minus capital F of s plus 1 divided by s. To prove this, we start with Mellin transform of integral 0 to x f t dt. This is given by, according to definition of Mellin transform, integral 0 to infinity x to the power s minus 1 integral 0 to x f t dt dx. If we integrate this by parts, then we obtain x to the power s by s integral from 0 to x f t dt t x from 0 to infinity minus integral from 0 to infinity x to the power s by s into fx dx. This is equal to minus of capital F s plus 1 by s. If we assume that limit x tending to infinity x to the power s f x equal to 0, so that the first term vanishes and this term is the Mellin transform of f x, which can be written as capital F of s plus 1 by s. So, we have proved this result. In a similar fashion, it can be proved that Mellin transform of integral from x to infinity f t dt, this is equal to capital F of s plus 1 by s, provided limit x tending to 0 x to the power s small f x is equal to 0. This can be proved in a similar manner by writing Mellin transform of this function and then integrating by parts to get Mellin transform of this function integral from x to infinity f t dt, that will be equal to capital F of s plus 1 by s. Thus, in module 2 of chapter 8, we have learned some important properties of Mellin transform. With this, we conclude module 2 of chapter 8.